In the last few lectures, we have looked at radiative transfer in enclosures, and our primary focus was on the radiosity method. And this involved essentially inverting a matrix. And today, with the availability of high speed computers, inverting a matrix is a very easy job and done quite easily. So, most of the problems involving radiative transfer enclosures is solved by this method. But today I will talk about a method, somewhat older one, which has been used, called the integral equation approach. Now, this method is now not so popular because it is somewhat more tedious than the matrix method, but I would like to introduce the method because when we later go to study of gas radiation, we have to solve integral equations. So, it is good to get an exposure to the way of solving integral equations through a simpler example. So, in this example, we will first set up the problem. So, the idea is that if you have a surface, on that surface you have a location, and that we will call as r vector k. Everything is varying continuously here. So, the heat flux at that location I will use the symbol at that location is nothing but radiosity at that location minus the radiation. So, this formulation is no different from what we did earlier, except that everything is a continuous variable, not a discrete number. And we can also write the radiosity at that location is a function of the emission for a gray surface, everything function of the location r k, and of course, reflection. So, as far as the problem is concerned, it is identical to what we did earlier, except everything is varying continuously. The only important difference is the irradiation, the radiation coming into this location now will be an integral over surface j of the radiosity of surface j and the shape factor f daj dak times daj. So, this is the radiation leaving surface j, this is fraction arriving at surface k, and you are going to sum over all surfaces j equals 1 to n. This is integration within that single surface. And all of us know by now that this differential shape factor is a basic quantity which we know is cos theta k cos theta j by pi s k j the whole squared daj. So, this also is known. So, this is the formal statement of the problem, and as in the previous examples we have done, the aim is to know how the radiosity is varying with distance in each of the surfaces. Previously, we solved this problem by dividing the surface into discrete surfaces and then use matrix conversion. And as I pointed out, that is the preferred approach today, because matrix conversion is very fast and efficient with the use of computers. But imagine that you are asked to solve this problem more than 50 or 60 or 100 years ago, when you had no access to computers. Then you would have looked for some analytical way of solving this problem, and people managed to solve it without using computer. So, we just take a walk through history and look at how people solve this problem in the pre-computer era, and this will give us an insight into a method of solving integral equations analytically. Now, this is best done if we take a simple example. I will take a very simple example of a tube. Which is electrically heated from outside. So, you will come across this problem in many situations in which you have to heat a tube. So, certain amount of electrical energy is supplied here. So, there is a constant heat flux here supplied by the electrical heating, and you want to know the temperature of the tube. As a function of distance, and more specifically you would like to know where is the maximum temperature in the tube and what is upper limit of this temperature, so that you can choose a suitable material for this tube. So, in the simple problem we are going to do now, we will treat this ambient as at 0 degrees Kelvin. This is only for simplicity. Later we can easily extend this problem when the ambient is not at 0 degrees temperature. Now, let us say the tube diameter is d, length is L, and for convenience we will call this surface as 1, the other opening as 3, and the inner surface of the tube as 2. So, it is a 3 surface enclosure containing the inside of the tube and the 2 side openings. Okay. And you can see straight away that the heat flux to be supplied to the tube has to be equal to the radiosity of the tube, and we will measure all the distances as x from the end of the tube, and if we take an element here, that element is between y and y plus dy, and for convenience we will non-dimensionalize everything. Psi is x by diameter of the tube, and non-dimensional y is y by again t. So, these are non-dimensional quantities which makes our life a little easier, and the length by diameter ratio of the tube is small, non-dimensional number small l. So, with that you can see that the radiosity of this tube will vary with psi, and minus irradiation will be radiation leaving other parts of tube and arriving here, times the shape factor between d psi and d eta. Okay. And once you know this shape factor f d psi d eta and Q2 is given, specified electrical heating. Here, so, given Q2 and f d psi d eta, we solve for V2 of psi. So, that is a problem statement, and you can see that this is an integral equation, because the unknown function is inside the integral. This is not commonly taught in most colleges. You are taught how to solve differential equation, you are taught how to solve algebraic equations. Very rarely you are taught how to solve integral equations, where the unknown function is inside the integral. So, that is the purpose of this particular example, to tell you how you could solve the integral equation. Now, before we go to that, we need to look at this, what is called kernel. So, in integral equation, you have the unknown function here multiplied by a kernel, and the function also appears outside, and that is a non-homogeneous term, which is the specified heating. So, what is this kernel? This kernel you can easily obtain from standard tables for shape factor. So, f d psi d eta will be equal to 1 minus modulus of squared plus 3 by 2 modulus of the difference in distances, and at the bottom we have and the entire thing is of course multiplied by d eta. So, this is the typical nature of the function, and you can imagine that this will not be easy. Once this is plugged into that equation we wrote down, it is not easy to solve this equation analytically. It can be solved numerically. There are lots of techniques available, and that is not the aim of this lecture. The aim of the lecture is to find a way to solve this analytically, because that gives more insight into the solution. So, we go for what is known as exponential kernel approximation. So, this kernel we want to approximate it as an exponential. Now, the logic here is, you can see then when eta equals psi, you can see that f d eta equal to essentially 1 into d eta. Now, as you go further away, as eta minus psi increases, f d eta d psi tends to 0. So, this function has a largest value when eta equals psi, and as eta and psi, if you recall the eta and psi, though that you have not forgotten what we wrote in the last figure. So, there is one element here, another element here. This element which is psi and psi plus d psi, this is eta. So, when these two elements are far apart, then the shape factor between these two will be very low. When they are next to each other, that is when the shape factor is maximum. So, now we want to replace this function by an exponential, and for this case the exponential approximation is that f d psi d eta is approximately equal to e to the power of minus 2 times eta minus psi. Now, you might wonder how we arrived at this approximation. Now, there are actually two things involved. Actually, we assume that f d psi d eta is approximately equal to a times e to the power of minus b mod of eta minus psi, and we need to find these two quantities. From the original function, we know that when eta equals psi, this function is 1. So, we want to keep a equal to 1 if possible. After that, we need to find b, and the b that you choose depends on what you want to, what kind of approximation you want for this function. So, b is chosen such that the integral of this quantity or the length, if you recall the previous expression. So, we want this integral to be same both for the actual kernel and the approximate kernel. So, so a and b are chosen so that at the origin it tends to, this tends to value 1, this quantity goes to 1, and as the distance between the two elements goes up, it tends to 0. So, I will now show a picture that illustrates that nicely. So, this is the tube that we looked at. This is the problem example. X the distance from one end and y the distance from the same end, and these are two elements, psi plus d psi and eta plus d eta, and you can imagine the flux is going to vary somewhat like this. That is to be realistic, because right in the center of the tube we are not seeing much of the ambient. So, it will be the hottest and the flux will be the highest radiosity, and as you go to the edges where you are seeing a cold background here, that the radiosity will come down. So, these two are understood. Now, we go to the next picture. Here we show how we have made the approximation. The approximation that we have made, the solid is the actual function, the dotted line is an approximation, and you can see that by choosing a equals 1 and b equals 2, we have ensured that this function is slightly lower than the actual function between 1 and between 0 and 0.5, and beyond 0.75 it is somewhat higher, but the area under the curve is almost same. So, that is our main criteria. We want the function to correctly reproduce the behavior of the kernel at the origin. In addition, the only other constant we have, which is b, is so chosen that the area under the curve of the actual more complicated function and the exponential approximation should be same. So, you can see that this is quite good, the fit between the approximate function and the actual function, and so we expect that this will give us some useful result. So, now we go back to our solution methodology. So, once you make this approximation, you can write down the heat flux on the left hand side is equal to the unknown radiosity on the right minus. Now, since there is a modulus function involved, it is better to split the integral 0 to L into two parts, 0 to psi, then you have the unknown radiosity e to the minus. Now, since modulus is involved and you are dealing with psi less than eta, so this will come out as psi minus eta into d eta, and the second term will be minus going from psi to L, again b 2 of eta e to the power minus 2 eta minus psi d eta. So, all we have done is to avoid the modulus term, we have split the integral 0 to L into two parts, 0 to psi and psi to L. So, in both cases the exponential is decaying, which is to be believed in, and now we have the full integral equation in front of us. Now, one of the great advantages of choosing an exponential kernel approximation is that the exponential function repeats itself on differentiation. Okay. So, that advantage we want to exploit. Our aim is to convert the integral equation to a differential equation. That is because we know well known techniques to solve differential equations. All of you have studied it. On the other hand, very few have a mastery of methods of solving integral equations. So, if you can convert the integral equation to a differential equation, then you can use the standard techniques that you have learned as well as easily available in the literature. So, how do we get a differential? We have to eliminate these two integrals. Now, you can see very easily that when you differentiate this function twice, the exponential will repeat itself, and then you subtract the equation you have obtained after two differentiation with the original equation, all the integral terms will disappear and you will be left with the differential equation. So, this is the right. Now, before you go further, we need to know a little bit about what is known as the Leibniz rule. Now, Leibniz rule is concerned with the following issue. Suppose you want to differentiate an integral where the limits of the integral are function of x and inside there is another function of x, y and dy. So, what is this? The Leibniz rule states that in order to differentiate a function in which the limits of the integral are itself not a constant, but functions of this quantity function of x, you have to first differentiate this function and evaluate this function at y equals b minus differentiate this function, the lower limit, evaluate the function the lower limit, and then you can take the differentiation inside. So, Leibniz rule lays down the condition that you cannot just merely take the differential from outside to inside the integral if the two limits in the integral are not constants. Many of you may have done it because you may have dealt with limits which are independent of x, in which case these two terms drop out and you are left with this. This all of you are familiar with, but many of you may not be familiar with the situation where the limits of the integral are not constants, but functions of the outside variable. Now, let us apply that to one of the examples. Suppose I want to know what is d by d psi of 0 to psi b2 of eta e to the power minus 2 psi minus eta d eta. What is this? Here you see that the upper limit psi is a function of this quantity. So, in applying Leibniz rule, you have to say d by d psi of psi, which is 1, and calculate this function at eta equals psi, that is 1. So, you are left with b2 of psi. Then this of course does not contribute to 0, does not contribute anything, that is not a function of psi. Then you take the integral inside, then this differentiation comes in, give you minus 2. So, it is minus 2 into 0 to psi b2 of eta e to the power minus 2 psi minus eta d eta. So, we have done the differentiation. Similarly, we have to do the differentiation for the other function that is there, where the lower limit is a function of psi. Now, we do this twice. Okay. When you do this twice, I will and you do this twice and you subtract it from the original integral equation. These terms will cancel out. okay, because when you do two differentiation of exponential, then in the first one you have minus sign, you differentiate again, you get a plus sign. So, finally, you are left with a function same as the function that you see in the first equation. When you subtract the twice differentiated function from the original function, all the integral terms cancel out. I suggest that you do it as an exercise on your own. It is a good learning exercise, and you will see that you can eliminate the integral. And when you eliminate the integral, finally, you are left with a very simple equation. It is t squared b 2 d psi squared is equal to minus 4 q 2. So, the integral equation simplifies to a differential equation, because we have used the exponential approximation, where the kernel is repeating itself. Now, what are the boundary conditions? Of course, this is a differential equation, all of you know how to solve it, and after solving it, you will have two constants. Let us differentiate once. dB 2 d psi is equal to minus 4 q 2 psi plus c 1. Okay. Now, the problem that we have stated is symmetric. So, by symmetry, we know that the radiosity has to reach a maxima at the middle of the tube, because all of you see that the tube is there. We plot the radiosity, it will be like that, and right at the center of the tube at L by 2, it will be a maxima. So, the slope will be 0. So, if we take that at psi equals L by 2, this is 0, we get C 1. Okay. So, C 1 becomes 2 q 2 L. You put L by 2 here, you get that side. So, this is the value of C 1. Then you integrate once more. Okay. Now, integrate once more, you get P 2 of psi is equal to minus 4 q 2 psi squared by 2 plus 2 q 2 L psi plus C 2, one more constant. How do you find this constant? We do not see any other boundary condition which is easily available. We exploited symmetry, but we have no boundary condition either at x equals 0 or x equals L, we do not have it. But although we do not have boundary condition, the original equation that we wrote down has to be satisfied at all points. So, one way to do it is to satisfy the original differential equation original integral equation at some psi. Let us take psi equals 0 just for convenience. So, we know that q 2 of 0 has to be equal to P 2 of 0 minus 0 to L B 2 of eta e to the power minus 2 eta d eta. We know that, okay, at psi equals 0. So, now you plug this expression into this integral, integrate, and when you do that, you will get the expression for B 2 of 0, okay. That is C 2. You will get the expression for C 2, and that concludes the problem that we need to solve. So, we saw that there were two constants we obtained because we had a second order differential equation. One constant came from symmetry and the other constant came by satisfying this equation. The integral equation at some point can be at psi equals 0, psi equals L, or even psi equals L by 2, anywhere, it does not matter. You satisfy it at one point and put this function back in it, integrate it, you will get C2. So, you will get the final solution for the radiosity, and you can then even estimate the actual temperature that is obtained in this result. Now, so having solved this equation now, we can now ask ourselves that this problem that we solved, the final result, so that you can check the result that we got, will be B2 of psi is equal to Q2 into L plus 1 plus 2 into psi L minus psi squared. So, once you get C2, this answer should get, and you can verify that dB2 d psi is indeed 0 at psi equals L by 2. That you can see easily because dB2 d psi nothing but 2L minus 2 psi, and then you put psi equals L by 2, and right you can see get L minus 2 psi, psi L by 2, L minus L is 0, and this thing becomes 0. Okay. So, this is a final result for the variation of radiosity with length, and once you know radiosity and you know the imposed heat flux, you can also calculate temperature. So, this is the method that we have shown for solving enclosure problem, where the variation radiosity is continuous and where you are able to use the kernel approximation, then you are getting complete analytic solution for radiosity, for temperature, and any other property that you might want to derive. So, this is a interesting result, of course, a very special case, and these results are very useful to us, because tomorrow when you solve this problem numerically using radiosity method and matrix inversion, you would need to verify your solution against some other solution. At that time, this kind of problem will act as your test case. You may divide this tube into 100 parts and have 100 radiosities, invert a matrix, get the radiosity, and ultimately plot the function and see how close it comes to this expression here. So, these are very useful results that you obtain analytically, which can be used to tune your code, because when you solve the problem numerically, you have to make various judgments. You have to decide if you want to divide the tube into 100 parts or 1000 parts before you do matrix inversion. Now, that really depends upon what kind of accuracy that you want to attain. So, accuracy goal has to be stated clearly, and once you state your accuracy goal, then you can decide. Suppose you want either radiosity or temperature accurate to 1%, then that will determine how fine you want to divide the tube into many parts. So, this analytic solution will help you to come up with the appropriate number of discrete elements you need to have in that solution. So, we gave the example, although this example is somewhat simple, but it illustrates the usefulness to have a few analytical solution which will enable you to compare the standard numerical results with analytical solutions. Now, with that we conclude for the time being our discussion on the enclosures. Now, we move on to a very important topic. So far we have looked at radiative transfer in surfaces, radiative transfer between surfaces using the concept of shape factor and enclosure. So, we have given a fairly a good survey of what is going on in this area, but the most important problem that we have to deal with now is gas radiation. So far we had assumed that radiation leaving a surface, and when it reaches another surface, in between there is no medium which absorbs or scatters radiation. Now, we want to tackle the problem where we want to look at an absorbing scattering medium between two surfaces, and we want to know how it attenuates radiation and how to calculate that attenuation. If you recall, the basic concept of intensity in a given direction, given wavelength was so defined that when this radiation is going through a medium where there is no absorption and scattering, this remains constant. If the medium through which it is going is non-absorbing and non-scattering. So, now we ask ourselves, what will happen to this quantity if the medium is absorbing and scattering? Okay. So, if the medium is absorbing and scattering, then immediately you can see that this quantity cannot be constant, because if you think this is a stream of photons, some of the photons will be absorbed, some will be scattered out, and some of the photon will be scattered in. So, we have to account for all those features. To do that, we need some basic laws and definition to proceed further. So, let us think of a very simple example of a medium of thickness dx, and the radiation intensity arriving at x is that, and what is going out at x plus dx is something else, and the two are not equal. So, the change in intensity in these two is obviously d I prime lambda. Now, the question is, what does it depend on? What does the change in intensity depend on vis-a-vis the property medium? One thing you can easily see that the intensity must decrease, this quantity has to be negative, that is quite clear. Secondly, it has proportional to the thickness of the element, that is quite obvious. The thicker the element, there will be more absorption, more scattering. So, we expect the change in intensity has proportional to the thickness. Now, it also will proportional to the incoming intensity, because this intensity is a measure of the photon flux. So, if there are more photons, there will be more decrease of this intensity. So, if there are 100 photons here and 10 photons gets absorbed as it goes through the medium here. Now, there are 400 photons, you expect 40 photons to be absorbed. So, that is expressed to the fact that d I prime lambda is proportional to I prime lambda and the thickness of the element. Now, there is something in the front of this which is an unknown, and which is what we call the extinction coefficient. So, this statement we are saying is that the change in intensity in a given direction wavelength is proportional to the incoming intensity, proportional to the thickness of the element, it is negative because it is decreasing, and the proportionality constant is called the extinction coefficient. Now, this is sometimes called as the Beer's law or Boger's law. That is a matter of which textbook you look up. Now, this law was discovered by many people in different branches of science. This has been used by people dealing with illumination and optics. It is used by people who do astrophysics. This is also used by people who do radiation furnaces. So, and of course, it also used in nuclear radiation laws. So, this law has been discovered in a wide variety of contexts, and some of them called the Beer's law or Boger's law. The name is not that important, except that this law follows logically. We can verify this law in the laboratory doing experiment, but what we have stated so far is follow essentially from common sense, because you are expecting the decrease in intensity depending on the thickness of the layer and the incoming radiation, and the proportionality constant k lambda is called the extinction coefficient. This extinction coefficient has two parts. One is absorption coefficient, other is the scattering coefficient. And note that as per this equation, this quantity has to have units of meter minus 1. So, that this product is non-dimensional and this same as this. So, extinction coefficient is a very important thing, because 1 over extinction coefficient can be thought of as mean free path of the photons. That is the mean distance that a photon travels before it is absorbed or scattered. So, this quantity is very useful quantity, because if k lambda is shown to be 1 meter minus 1, then we say that photons travel approximately 1 meter before they are absorbed or scattered. So, that is our physical understanding of k lambda, that is 1 over k lambda is a measure of the approximate distance on an average that a photon travels before it is absorbed or scattered. And it is sum of two quantities, the absorption coefficient, wherein the photon is absorbed by the material and disappears from your calculation, or the photon traveling in a given direction suddenly changes direction and goes in some other direction. So, as far as this direction is concerned, you have lost that photon. So, once the photon is scattered out, it is not following this path that we have enunciated. This path is going in some other path, some other direction. So, as far as this direction is concerned, we have lost a photon, because it is scattered out of this direction. Now, in this first part of the course, we will focus primarily on the absorption coefficient and take up scattering much later in the course, because much more complicated, much more involved quantity. So, absorption is our major focus. The absorption coefficient of a gas or a medium, as you can imagine, is a function of many things, of course, function of wavelength that I will talk about, function on the temperature of the medium, obviously, depends on the total pressure, depends on the concentration of the individual gas. So, somebody has to provide this function, how the absorption coefficient of a gas or any other medium depends on temperature, total pressure and the concentration of gases or particles. Once that is given to you, this function, then of course, the rest of the problem we will see is quite straightforward. But I must mention that this is the most difficult quantity that we deal in radiation, because A lambda is an extremely strong function of wavelength. It varies very rapidly from as you go from one wavelength to other. So, it is a very extremely complex function, and hence a lot of time has been devoted by hundreds of people over a large period to find out how to solve this problem, wherein the function basic function we have got A lambda is an extremely strong function of wavelength. It will go to very high value, then within a few 0.5 or 0.2 micron it will come down to almost transparent. So, essentially A lambda fluctuates very rapidly, and that, as all of you must now realize, is not something a computer likes. Computer likes functions which are monotonic in nature, which vary slowly and which can easily be represented by some simple function. But unfortunately, radiation transient gases A lambda, as you will see later, is an extremely complex function of lambda. So, it is not easy to specify the function in the classroom. So, we will spend some time later in this course asking how this function varies with lambda and how we ultimately handle this complexity which is inherent in gas radiation heat transfer. Now, the only puzzling part about this result I have written is the dependence on total pressure, and this of course depends on partial pressure of the gas. So, the absorption coefficient of gas depends not only on temperature, but both on total pressure and partial pressure. So, this is the dependence which confuses most students. For example, suppose you have a mixture of nitrogen and carbon dioxide in a container. Nitrogen is transparent to almost all radiation, but carbon dioxide is a strongly absorbing gas in the infrared. Okay. So, although N2 does not directly absorb any radiation, because it is a linear triatomic molecule, linear diatomic molecule, we have to figure out what role nitrogen is playing in this mixture. Nitrogen itself will not be able to absorb any radiation because it is a linear diatomic molecule, but it can assist carbon dioxide in trying to absorb some radiation. So, the way nitrogen indirectly affects absorption of the infrared molecules in this situation, you have to understand that what nitrogen does is it collides with carbon dioxide and broadens the absorption curve of that mixture, and so higher temperature and higher pressure are always preferred when people want to calculate the absorption coefficient of a mixture of gases. Now, this concept will be dealt with in great detail later in this course, when we look at how to get this function A lambda. But right now, we will look at a non-scattering medium, that is neglecting scattering function, and we will look at absorption function and go back to our original equation which we wrote down, which is d I prime lambda dx is equal to minus I prime lambda. Now, this quantity deals only with absorption, okay, and so we will write into A lambda. No scattering is looked at right now. Now, all of you know by now that any medium, liquid, solid or gas, if it is absorbed radiation, it will also emit radiation. So, we have to put an emission term here, which we had so far not mentioned. So, the way to look at this, the change in intensity while going through a certain path is equal to loss of intensity due to absorption and some gain in intensity due to emission. So, the real rate of change of intensity will depend both on the loss of photon due to absorption as well as the gain that may occur due to emission by the photon. So, essentially what you are looking at is there are photons come in here, partly absorbed and two of them come here, but can always have emission from inside which can add to that. So, that is the second term. Now, the question is how do you estimate the intensity of the emission by the gas? For that, we are going to appeal to Kirchhoffs law. All of you know that if you neglect the term and solve for I prime lambda, it will be solved, it will be I prime lambda of 0 e to the minus A lambda x, assuming A lambda is a constant. So, in the absence of emission, intensity declines exponentially, and how rapidly this exponential decay occurs depends upon the absorption coefficient of the gas and the length traveled by the radiation beam. So, this is a very important result and it is used widely in this field. But notice that we can also define absorptivity of this gas now. This is absorption coefficient, which is a dimensional quantity. We can also talk about absorptivity, which is a fraction of radiation that is absorbed. That is what was coming in and what went out divided by what is coming in. So, this is absorptivity. Now, if you remember your Kirchhoffs law, the directional spectral absorptivity has to be equal to directional spectral intensity, emissivity. So, this is following from the most basic statement of Kirchhoffs law, that the directional spectral absorptivity and the directional spectral emissivity are equal. And if they are equal, then you can write the emission. So, you have 1 minus I prime lambda x minus I prime lambda 0. So, this we already solved, if you recall. So, we will get in the absence of emission this kind of simple expression for intensity. So, the final expression for absorptivity, if you substitute this here, is I prime lambda 0 we are going to write that alpha prime lambda is equal to 1 minus a lambda x. So, this is an important expression and this we know is equal to experimental emissivity. So, this is an important use of Kirchhoffs law for gases. We will continue this lecture next time, where we will use this Kirchhoffs law to estimate the emission intensity, which we are not included in the first derivation.